Well, it seems that the old Thrivemeister wants to science. Isn't that adorable? A couple of weeks ago, Thrivey did an experiment to attempt to show that the moon emits cold light. He said he was going to chop this video down and make the data available. None of that's happened yet, so to spare you the agony of watching his entire live stream, I'll show you the results such as they are. But first, a bit of covering my ass.
And again, there's no issues with me with copyright or anything like that. Share this everywhere.
Rather than just go through his video from start to finish and point out all the absurdities in his experiment as they occur, I'll break this down into a couple of parts. First, I'll look at his experimental setup, his equipment, etc. Next, I'll look at his methodology. This would include things like how were the measurements taken, what steps were taken to avoid measurement errors, etc. Next, I'll look at his results and what conclusions he's drawn from them. And finally, I'll suggest some ways that he could improve his experiment. Before going into the details of his experiment, I have to ask, what's the point? Let's say, for the sake of argument, that Thrivey's experiment is successful and it shows the moon emits cold light. So what? All that this shows is that there is some hitherto unknown property of moonlight that warrants further investigation. It doesn't say anything about the shape of the Earth. In his video, Thrivey conducts several experiments. He has one primary experiment and a few supplemental ones. I'm only going to go over his primary experiment here, but later in the video I'll describe some of his other ones. Spoiler, only one of the supplementary experiments is of any value, and it's probably more useful than his main one, but I'll get into that later. The basic setup is a vertical board with a thermometer on each side. One side of the board faces the moon, the other side faces away from it. This setup is acceptable. If done correctly, it will give reasonably accurate results. Note the qualifier, if done correctly. As I was saying, there would be a thermometer on each side of the vertical board. The thermometer in question is the Protemex MS6508, which is just a rebranding of the Mastech MS6508. This would be a suitable choice of thermometer if Thrivey didn't do something stupid.
We can remove the cap and get the sensor to be exposed to the moonlight directly.
That's right, Thrivey is so arrogant that he thinks he knows how to get more accurate readings from the thermometer than the manufacturer. While I couldn't find any details of the sensor being used, from appearances it seems to be an infrared sensor of some sort. So why does this matter? Judging by appearances, the way this thermometer works is the temperature of the plastic cap equalized to the ambient air temperature, and the sensor measures the temperature of the plastic. You can see that the cap is vented, which allows the air temperature inside to be the same as the air temperature outside. So what happens if the cap is removed? Simple. The sensor reads the temperature of whatever is in front of it. As such, a person standing in front of it will impact the temperature reading. Keep that in mind when you look at his temperature readings. So, he designed an experiment that would work reasonably well if he hadn't pissed around with a thermometer, rendering them nearly useless. Let's see what he does with it. The first thing Thrivey does is get readings to calibrate the thermometers. That's good practice. I'm not sure why he's keeping track of humidity, but sure, why not? Perhaps he thinks moonlight dries the air too. So, what are his calibration readings?
74.8 and 24% humidity. 75.2, a little bit. This is the one that's totally in the dark, so it's a little bit higher. 75.2.
The thermometer that will initially be in the moonlight reads 74.8 degrees, and the one that will initially be in the dark reads 75.2. I say initially because partway through the experiment he inexplicably spins the entire setup around so that the thermometer that was in the moonlight is in the shade and vice versa. For clarity, the thermometer that is initially in the moonlight will be called thermometer A, and the one initially in the shade will be thermometer B. This means that for calibration, thermometer A had a reading of 74.8 plus or minus 0.1 degrees, and thermometer B had a reading of 75.2 plus or minus 0.1 degrees. So, during calculations, I'll need to add the difference between these two readings, C equals 0.4 plus or minus 0.2 degrees, to the reading from thermometer A before comparing it with the reading from thermometer B. Also, since the expectation is that the shaded side should be warmer, all of my calculations will be the shaded side minus the moonlit side. This means that initially it will be delta T equals B minus A plus C, or B minus A minus C. After he, for some reason, spins the entire thing around, the difference in temperature will be delta T equals A plus C minus B. With that out of the way, let's take some actual measurements.
But we've got 71.4 degrees already in the moonlight. I think we had 73 over there in the shade, but anyway, 71.2 roughly. And this is what we have on the other side. On the other side, we have 72.3.
Okay, that's thermometer A reads 71.2 degrees and thermometer B reads 72.3. A quick calculation shows that the moon side is 0.7 plus or minus 0.4 degrees cooler. Well, that supports Thrivey's hypothesis with an experimental error that the moonlit side should be cooler. He records more temperature measurements using this method, but first he shows a different method that he'll also be using.
To be placing the stick on the board, and then I'm going to hold the laser right to the edge right there, and then I'm going to shoot the plastic right in the middle and get a temperature reading.
That's the proper way to take a measurement. Use the same thermometer so there's no need for calibration measurements, keep a consistent distance between the laser and the target, and measure the temperature of the same material. Now let's see the results.
67.9 roughly on that one. Then I'll go around to the other side, and I'll hit the exact same material, the exact same plastic from the exact same distance, and get a temperature reading. This is 67.3. Now,
the temperature on the moonlit side is 67.3 degrees, and on the shadow side it's 67.9 degrees. Again, there's a 0.6 degree temperature difference in his favor, but did you see it? Let's have another look. On the dark side, he heats up the surface of the plastic with a bright fucking light. On the moonlit side, he carefully keeps the light off of the plastic. That could easily account for a 0.6 degree temperature difference. Next, he shows a couple of his little side experiments. They're hilariously absurd and pointless. I'm not going to waste your time with them, but if you're curious, you can check out his original video, link in the description. He starts talking about them at around 6.5 minutes in. While he's showing these side experiments, we catch a glimpse of another thermometer like the ones he's using in his main experiment sitting on the table.
by the way, on the table we have just a thermometer to register the ambient air temperature. It is exposed to moonlight. But it's just out in the open, and that's just to say, okay, our ambient air temperature dropped 2 degrees, but the ones on the board dropped by only 1 or 4, whatever.
Notice the temperature on it. It's 65.3 degrees. This is consistent with the temperature you got using the laser thermometer, not the other thermometers which show a temperature of over 70 degrees. This, like so many other things, calls into question the measurements he's taking. With that out of the way, let's take some more measurements and see what happens.
So I'm going to start this time with the thermometer. Let's start with the thermometer in the shaded area, not exposed to the moon. And we have 74.1 degrees. So this is the dark side. 74.1 degrees, and the relative humidity is 24.6%. Now you'll see these figures jump around a little bit, but they're always within a couple of points. So 24.6%. And now we're going to go to the moonlit side. And step there. And we're going to get its temperature, which is 71.7 degrees. And the relative humidity is 26.9%.
Thermometer B reads 74.1 degrees, thermometer A reads 71.7 degrees. A difference in his favor of 2 degrees. But again, did you see it? A bright light frying the thermometer sensor. He carefully keeps the light off the sensor on the moonlit side. You can actually see that it makes a difference in the temperature. Let's watch it in slow motion when he takes the light off the sensor on the dark side. Did you see it? As soon as the light came off the sensor, the temperature starts to drop. Next, he takes another reading using his laser thermometer.
So again, I'm going to place this stick right next to the material. I'm going to put the very front end right on the edge of the stick, so it's 10 inches exactly. The center of the plastic piece where the temperature is given is 65.8 degrees. So I'm going to mark that down. That's 65.8. And that's on the dark side. And on the moonlit side, of course, we're causing some light pollution here, but we'll leave it alone here in a second. Same thing, using a 10-inch measuring stick, placing it to the edge and shooting it 65.8 degrees.
This time both sides have the same temperature, 65.8 degrees. Also, this time, if you noticed, he kept the light off the surface being measured. Let's take some more measurements.
Okay, it's 8:13, so it's 10 minutes later. I'm going to redo the test. 8:13. Excuse me. And we started with the dark side before, so we're going to start with the moonlit side this time. And see what we get. We have 71 degrees Fahrenheit, 71.2. I think my fingers made it go up a little bit, maybe. Or we're blocking the moonlight. We should back up a little bit. All right, let's go with 71.
There might be a little bit of that light too.
Yeah, 71.6. We're going to use the higher number. So 71.6, and the humidity was 26.6. And let's go over to the shaded area. And we've got 72.6.
At this point, Thrivey spins the whole experiment around so that thermometer A is on the shaded side, thermometer B is on the moonlit side, and takes more measurements.
Which I guess we'll do that. You want to do that now?
Sure.
All right, let's switch it around. So
Let's loosen him and spin the whole thing.
there we go. Very easy to do.
He lets the thing sit for a while and takes more measurements, starting with the laser thermometer.
Measuring stick. Right on the middle of the plastic. 63.2 degrees Fahrenheit. Okay, so that's on the dark side. 63.2. Let me try it one more time because I didn't like the fact that it didn't move. Now it's moving. I'm going to call that 63.8. Close to before, but at least this time it moved. Before it was kind of locked. So 63.8. Come over to the moonlit side. Wow. Moonlit side was showing 69. I know the other was 70 something, right? 71. So this is 63.8. 64. Let's try it again. This is 64. So I think.
Notice how the temperature was originally 63.2 degrees, then when he turned on the backlight, it jumped to 63.8. That tells me that the backlight increased the temperature by about 0.6 degrees. Because of this, even though Thrivey calls it 63.8, I'll call it 63.2. This is the last measurement he takes using the laser thermometer. You're going to love the reason for this, which he gives near the end of the live stream. I'll get to that in a bit. Now he takes more measurements with the other thermometers. I'm not going to bore you by showing all of them, but after the last of his measurements are taken, he decides to completely change the geometry of the experiment and tilts it so the moonlit side is pointing up and the shaded side is pointing down.
Let's tilt it back if we can.
Okay.
And so it's actually in the moonlight like it was earlier. Definitely, as you can see, tilted. However, even though it's tilted like this, there's no overhang. There's nothing to stop any heat.
Go ahead and hit some bright light over there so they can see.
But again, I think we have to do this now just because it's later in the night.
That's right, folks. He's pointing one of the thermometers down toward the ground, which is radiating heat, and the other one away from it. What do you suppose is going to happen? If you guess that the one pointing to the ground will be warmer, give yourself a prize.
In the shade, we've got, I'm going to hit this real quickly, 70.7 degrees, 29.2. 70.7, 29.2, that's on the dark side. Anybody got the time?
If you double tap it, sometimes it will focus. 8:54.
8:54, thank you. And now the moonlit side.
I can't see it.
Yeah, you need
And the moonlight side is 67.8. What a difference it makes pointing it at the moon.
Yes, what a difference it makes pointing it at the moon. Yeah, one thermometer pointed at the heat source, the other one pointed away from it makes a difference. No shit, Sherlock. In the end, Thrivey took 7 measurements with his main experiment and 3 using the laser thermometer. Because of his modifications to the thermometers, the results of his main experiment were, at best, inconclusive. The thermometers were being affected by their body heat and their lights. This table summarizes his measurements. For the first 3 measurements, A is on the moonlit side, B is on the dark side. This switches around for the next 4 measurements. The difference is the amount by which the dark side is warmer than the moonlit side. This varies from slightly warmer to slightly cooler. Unfortunately, because no precautions were taken to eliminate sources of error, for example, body temperature and lights, as well as tampering with the thermometers so they no longer conform to manufacturer specifications, these measurements are worthless. What about his laser thermometer? He made 3 measurements with that thing. What were the results? These are more reliable measurements for reasons that I went over earlier, but Thrivey decided not to continue with them because, as he puts it,
I would say the laser test was inconclusive at best. It didn't really show anything.
That's right, because they didn't support his desired conclusion, he basically dismissed these measurements. You know, like science doesn't. In fact, if you look at the temperature showing on the thermometer that was just sitting on the table, it conforms to these temperatures more closely than it does to his main experiment.
Which
Oops,
it goes
it
back
went to Celsius.
Yeah, 64.7 degrees.
Given all of this, the most charitable thing I can say is his experiment was inconclusive. Interestingly, though, his experiment was surprisingly close to being not shit. So what could have been done to improve his experiment? Well, first and foremost, don't piss around with the thermometers. The plastic cap was put over the sensor for a reason. The cap reaches the ambient air temperature, and the sensor measures the temperature of the plastic. You even recognize that this thermometer was directional. That's why you pointed at the moon instead of just keeping it horizontal. Couldn't you, from this, realize that it was also picking up your body temperature? That's why your temperature measurements from these thermometers was so much higher than from every other thermometer that you were using. Next, you need to eliminate potential sources of error, bright lights, etc. Shining a light on the thermometer sensor will affect your results. Light is energy. Increased energy causes increased temperature. Since the temperature differences you're dealing with are small, you need to be careful to reduce or eliminate any source of temperature change other than the one you're trying to measure. By now you're saying, okay, smart guy, you're such a genius, why don't you tell us how you would do it? Well, fine, if you're going to be like that, I will. Most of the experiment can be kept as is. I have no real problem with it. The only changes I would make are, 1. Don't tamper with the thermometers. They're designed that way for a reason. 2. Keep using the laser thermometer, but have a designated spot on which to make the measurements. For example, block off an area with masking tape or something away from other equipment and measure the temperature on that spot. 3. Get rid of the fucking lights. Light equals heat. Shining lights on everything will cause their temperature to change. Don't do it. 4. Don't modify the experiment partway through. There was no reason to spin the whole thing around after the first 3 measurements. 5. Take measurements of everything that might impact your experiment. For example, measure the angle between the moon and the vertical board. If the moon, as you assert, emits cold light, the temperature difference should be impacted by the angle. 6. Do the identical experiment on a night when the moon isn't visible. For example, 14 days later, the moon will be visible in the day rather than the night. This would be a useful control. Implement some of these changes, and there's hope of getting reliable results. Anyway, that's all I can be bothered with. He does all kinds of other stupid things that I didn't have time to go into. Watch his video if you think he can stomach it. Otherwise, click like, or don't. Subscribe, or don't.